All right, 7.4 video notes, properties of similar triangles. So we're going to learn a few theorems today to try to figure out pieces of triangles that are in proportion with each other. So I think there's actually two theorems and one converse that we'll jump into today. So we're going to use properties of similar triangles to solve problems. There's several theorems here. And the first one is, most textbooks don't call it this, but it's referred to as the side splitter theorem. I thought maybe you would remember the side splitter theorem. It'd be a better name than some other name. So here's what we're going to do. We're going to draw a triangle over here to the side. So we draw some sort of triangle, nothing really special about it. And we'll label this thing, A, B, C. And then what happens, let's just say that a line comes in that's parallel to one of the sides. So for instance, let's say that we draw a line that comes through here. And let's just call that line, I don't know, we'll put a couple points here. We'll call this D, and we'll call this point E. And in order for this theorem to work, we have to know that DE is parallel to CB. And it split the sides of a triangle. That's why it's called the side splitter. Well, in the side splitter theorem, basically says if a line is parallel to a side of the triangle, then the sides are in proportion to each other. They're split evenly in proportion with each other. So what that means from this picture is that, so side AC got split, not in half, but just split somehow. So the distance from A to D compared to the distance from D to C, all right, so basically these two pieces over here, AD and DC, whatever that ratio is, it should be the exact same the other side, AE to EB. AE to EB. So that's what's referred to as a side splitter theorem. The two sides that got split are in proportion to each other. Top over bottom and top over bottom. So let's go down here to the bottom. Let's try to work a couple examples and see if we can put that into play. See if we can apply that and use it here. So example 1 in the diagram, it looks like the if part of our theorem is okay. We do have parallel lines, so if there's parallel lines, we can use what we were talking about. Well, the length of QU, I'm going to call that X. So basically, I can say that 10 is to X, 10 is to X, as 12 is to 6. And then we do our cross multiplying here. That's 12x, and this is 60. And we divide both sides by 12, and we end up with x equals 5. So 5. And that kind of makes sense, because when I look at my drawing here, these are nice numbers in the fact that the bottom part is half of the top. So this bottom part is half of the top. I probably could have just looked at that before I even started and skipped the whole cross multiplying in proportion once I saw that relationship, that 2-to-1 relationship. On this next problem, I really couldn't do that because I'm looking at 24 and 44, and there's not a nice double or a triple. So I'm going to set this one up the typical way. So we need to find KL, which I'm just going to call X. So I see my parallel lines. That tells me I can use the side splitter only if I have parallel lines. So I'm going to do 18 is to X as 24 is to 44. And this is going to require a little bit of work, a little bit of cross multiplying here. So 24x equals, get a calculator here and bust out some of these calculations. If on the homework at all you get decimals, let's just round to the nearest tenth. I don't know if we will here on the notes, but 18 times 44 is 792. And we divide both sides by 24. So divided by 24. And I get x equals 33. So KL is 33. Now, the converse of the side splitter theorem, remember what converse is? That just means you take the if and the then and you trade places with them. So basically the converse says is that if the sides are split proportionally, then the line is parallel. So it's a way to prove that two lines are parallel. You're kind of using the proportion to go backwards and show that they were parallel. Or in these above examples, we had to know that the lines were parallel to use the proportion. Now we're going to work backwards and use the proportion to show they're parallel. So let's kind of do that here in example 2. I need to show, or I need to prove that TU and WX are parallel to each other. Well, let's use the side splitter. So using the side splitter theorem, I'm going to start with, I'm going to say 6 is to 15 as 18 is to 45. And as long as this is a proportion, then I'm good. So there's a couple different ways I could check this. The easiest way I could check by number 1, do cross products. Do the cross products and see if they're the same. So 15 times 18, that would be, I believe, 270. And when I go the other way, 6 times 45, that equals 270. So it checks out. Okay, so I know right now, yes, TU is parallel to WX because their sides are in proportion. Now I also could have done, another method could have been to do decimals. And when I do decimals, 6 divided by 15 is 0.4, and 18 divided by 45 is 0.4. So that would have worked. I also could have reduced these two fractions. 3 goes into both of these numbers. It would be 2/5, and then 9 goes into both of these numbers, which would also be 2/5. So I also could have used fractions and just reduce them. But those are 3 ways to check proportions and see if they are equal to each other. Alright, let's go to the back side. So kind of an example off of this one is this problem about a farmer. It said a farmer A's land is divided by an interstate. The distances shown are in meters. Find the distance between the north border and the south border. So on my drawing, ultimately the distance between the north and the south border is, I need to figure out how long this line is. Okay, that's the true distance between the north border and the south border. So let's kind of set this thing up. And this is kind of like the side splitter on steroids, because we have a triangle. All right, you have a triangle where you have multiple lines that are parallel to each other. I have a parallel line, and a parallel line. So I think what should be true is those blue pieces, and let's just call the missing piece here X. And my ultimate answer to the question is going to be however long 2000 plus X is. That's going to be the ultimate answer. But I think my setup is going to be 2000 over X has to be equal to, well, the other side of this triangle is 2500 is to 3000. And now I need to solve that proportion. So really, if I kind of cut out everything in the picture, I have a triangle where I have a couple side splitter things going on. I have this one right here, and then I have another one right there. And so basically I could do lots of different proportions on this thing. It's just got 3 pieces instead of 2, but I'm really not interested in what happens up here at the top. That's not part of the question. The part of the question is simply I need to know how far it is from here to there. So we do our algebra, and we cross multiply. I get 2500x equals, that would be 6 with a bunch of zeros after it. So that's 600,000. And divide those two out. 2000. Actually, I gotta have 6 zeros. I think I missed a 0 there. That makes it better. And divide that by 2500. And I get x equals 2400, which is not the answer to the question. That's simply what x is. So now the true distance out here, I have to add those two together, and I get 4,400 is my final answer. And I believe the distances are in meters. So the final answer to the question is 4,400 meters. So kind of a real-life example of the side splitter theorem. All right, we have one more theorem here we want to look at down at the bottom, and this is called the angle bisector theorem. So notice in the diagram over here to the right, I have CD is the angle bisector. I know this because of these two markings. The two angles are equal. So the theorem says if a ray bisects an angle, so that's my if part, and I can see that because of this right here, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. So it kind of gets set up like this. AD is in proportion with DB, so AD is to DB as, and since I was kind of working on, let's say, the top part of the red line and the bottom part of the red line, AD is on the top, DB is on the bottom, then I'm going to use the side on the top to the side on the bottom. All right, that's one way to do it. So basically I have piece over piece and side over side is kind of how it goes. Now I've seen this done other ways in other books where they'll say the piece is to the side, so AD is to AC as the piece to the side, and it should come out the same because if you notice when you do your cross products, AC and DB are being timed together, and then AD and BC are also being timed together. They're just in different spots, but it can work out either way. So you can either go piece to piece, side to side, or piece to side, as long as you kind of keep it in the right order. So let's go down and let's knock out this bottom two examples here. Shouldn't be too awful bad. I'll do one each way. So when I look at it, I'm like, okay, here is my angle bisector, and now I'm going to use the ratio. So I'm going to kind of call this maybe the left and this the right. So I'm going to do the piece from the left over the piece from the right equals the side from the left over the side from the right. Okay, so basically I'm doing left over right, left over right. And now I got to work in this, doing a little bit of algebra. So 21 times 16 is 336. And then when I go this way, I got to be sure to distribute. That's 28x plus, that's 60 and 24, that's 84. And now to solve this, I'm going to subtract 84 from both sides. All right, which gives me 252 equals 28x. And then I divide both sides by 28. Which is 9. X equals 9. And I think that's what they wanted. Now I can plug it in just to make sure. So 9 plus 3 is 12. So let's check this out. 12 left piece over right piece. 12 is to 21 as left side to right side. And if I check my cross products here, 12 times 28 is 336, and 21 times 16 is 336. So I know I did this problem right. The answer is 9. Over here, B is a little bit trickier. So let's kind of look at this one. I have the angle bisector. All right, and I'm going to do the left piece over, and then here's where it gets a little tougher. I don't have the right piece. All right, here's where I gotta be kind of clever. The total distance is 14 here. All right, so if the total is 14 and this piece is x, this piece on the right side must be whatever 14 take away x is. That's the tough part of this problem, getting that dimension. So I have left piece over right piece, and now I'm going to do left side over right side. And I'm going to do a little cross multiplying action now. 12x. Had a few people ask, does it matter which way you go with the x's? It doesn't matter when you cross multiply. Either one. Over here I'm going to get, that's 80 and 32, that's 112 minus 8x. Got to make sure to do that times both pieces. We'll clean this up. I'm going to add 8x to both sides, which is 20x equals 112. And divide by 20, divide by 20. And it looks like I'm going to get a decimal here. 5.6. Now decimals always make me a little bit nervous, so I'm going to go back to my original picture and I'm going to plug that in. So I'm going to plug in a 5.6, and then over here I'm going to plug in 5.6, which would be 8.4. Well, let's see if that works out. So left piece over right piece equals left side over right side. And let's make sure, we'll check our cross products and we'll see if they're equal. So 8 times 8.4 is 67.2, and then 5.6 times 12 is 67.2. So it looks like it checked out right. So that's using angle bisector. So the two big theorems involved splitting triangles are the side splitter theorem or the angle bisector theorem. And they're both kind of similar in how you set them up, and they're exactly the same how you solve them by cross multiplying. All right, so I think you got what you need to get started on the 7-4 practice when you come to class tomorrow. See ya.